Bismillahirrahmanirrahim. I am Mrs.Alia Jadoon from Army Public School and College Fort Road, Rawalpindi. I welcome FSC Part 2 Physics students in this online sport program 2020. This is the second version of Lecture 2 of Week 3 from Chapter 16 Physics of Solids, and the topic is Energy Band Theory, given on page number 252 to 254 of your physics textbook. After careful listening of this video will enable you students to describe the idea of energy bands in solids. You will also be able to classify the electrical behavior of solids as conductors, insulators, and semiconductors on the basis of this energy band theory. Now students, on the basis of our previous knowledge, we can say that molecules arrangement in the substances like solid, liquids and gases are not same. They differ from each other. In gases, the molecules are very far apart from each other and there is a weak intermolecular force between them. In case of liquid, the molecules have moderate arrangement. However, the intermolecular force is not strong enough to give the liquids a definite shape. In case of solids, the atoms are arranged so closely that electrons within the molecule atoms move into neighboring atoms orbital. We in this chapter have discussed about different aspects of the solid, like the mechanical properties of solid, the magnetic properties of solids, and here we are going to discuss about the electrical properties of solid. That is how a solid is responding when an external electric field is applied to them. Well, to our surprise, the electrical behavior of various materials which are solid by nature is very diverse. Some of them on the passage of electric current show a very good conduction like copper, gold, aluminium, etc. At the other extreme, some solids like wood, diamond, they are showing a very little conductivity ranging from 10 raised by minus 10 to 10 raised by minus 20 ohm per meter, and these are called the insulators. Solids with intermediate conductivities, they are given the name of semiconductors, and the common known semiconductors are silicon and germanium. The conventional free electron theory based on the Bohr model of electron distribution in an atom failed to explain completely the vast diversity in the electrical behavior of these type of materials. Now students, when we take a single independent atom, we know that its electrons are bound with the nucleus and they will have a definite energy level. When we are going to take a large number of the atoms and suppose we are going to bring them close to make a solid body, so the energy level of each single independent atom will now separate into large number of the sub-levels, which we are calling states, under the action of the forces which are exerted by these atoms in the solid. Now these permissible energy states are discrete, but they are so closely spaced that they almost appear to form a continuous energy band. And in between two consecutive permissible energy band, there is a region which is known as forbidden energy gap, and as its name implies, this band is forbidden, one without energy, hence no electron stays in this band. The valence electrons, while going to the conduction band, will pass through this forbidden energy gap. Now here I would like to also indicate a term which is Fermi level. This is the highest energy state which is occupied by an electron at absolute zero temperature. Now at zero Kelvin temperature in metals, this particular level, which I am calling Fermi level, is existed, and below this all the energy levels are totally filled within one electron, and above this all the energy levels are completely unfilled or empty. So we can say that this Fermi level separates the filled and unfilled levels. The filled levels are known as the valence band and the unfilled levels are known as conduction band. The electrons which are present in the outermost shell of an atom are called the valence electrons, and the energy band which is occupying these valence electrons is known as the valence band. Now this is the highest occupied energy band, and it can be either completely filled or partially filled with the electrons, but it can never be unfilled. The band which is above this valence band is known as the conduction band, and in this band the electrons move freely and they can conduct electric current through the solids. That is why the electrons which are residing in this conduction band are known as the free electrons or conductive electrons. Any electron which is leaving the valence band is accommodated by the conduction band. So the conduction band can be either empty or partially filled with the electrons, but it cannot be fully occupied. The energy band structure of solids can explain many of their electrical and optical properties. Band gap is basically the factor which is used for determining the conductivity of any metal, and it differentiates the metals into conductors, insulators and semiconductors. So energy band gap is usually referred to the energy difference between the conduction and the valence band. Now students, you can see on your screen the figure of energy bands in solids. In the figure you can see there are two bands are present which are known as conduction band and valence band, and in between conduction and valence band there is a forbidden energy level. Now students, we are going to see that how this energy band theory help us to classify the solid state of matter into conductors, insulators and semiconductors. Look at the figure carefully on your screen. Here, in case of conductors, you can see the conduction band and the valence band are so close to each other that they are almost overlapping each other, and the forbidden energy gap is absent or it is vanished. So the best examples of the conductors are gold, aluminum, copper, etc. In these materials, the free electrons availability at room temperature is quite sufficient. So the conduction will increase once the small number of the voltage increases. That is, when we are going to apply the external electric field to these materials, what happens? The free electrons in the valence band quickly jump into the conduction band and they will start constituting the electric current. Students, we know that insulators are those materials in which the valence electrons are bound very tightly to their atoms and they are not free. The valence band is completely filled, so there are no vacant allowed energy levels which would allow the electrons to gain energy from an applied electric field and move from an occupied state in one atom to an empty state in another atom. Now, if you look at the figure carefully on your screen, you know that in case of insulators, the conduction band and the valence band are lying far apart from each other and there is a huge forbidden energy gap present between them. So it is practically very difficult for the valence electrons in the valence band to excite to such an extent that they can jump from this forbidden energy gap and occupy some position in the conduction band. We know that thermal excitation is a random process, so sometimes electron may get energy boost, but this band gap in an insulator is so great that probability of an electron jumping into the conduction band and then becoming a useful charge carrier is virtually zero. So in the valence band, the electrons are unable to gain the energy from an applied electric field as there are no vacant energy level for them to jump into. So this explains the extremely high resistivity and low conductivity of many insulators. Now, on the basis of energy band theory, we are going to discuss another very important class of solid materials which is known as semiconductors. Semiconductors are those materials which at room temperature have a partially filled conduction and a partially filled valence band, and there is a very narrow forbidden energy gap present between conduction and the valence band. Now, when the temperature is 0 Kelvin, all the valence electrons are bound to their position and there is no electron present in the conduction band. So at this temperature, the semiconductor material will behave like a perfect insulator. Now, when the temperature of the semiconductor material is increased, these electrons present in the valence band will get sufficient thermal energy to be excited and jump across this forbidden energy gap and occupy some position in the conduction band. Now, the electrons which are leaving the valence band, they will create a vacancy of electrons in the valence band. The vacancy of electron in the valence band is given the name of hole, and it behaves like a positive charge. Now, when we connect a battery across the semiconductor material, it establishes an electric field across it, due to which a direct flow of electrons and holes take place. The electron will drift towards the positive end, whereas the hole will drift towards the negative end of the semiconductor. So, the current flowing through the semiconductor is carried by both the electrons and the holes. The electrical behavior of semiconductor is substantially changed on introducing a small amount of impurity into the pure semiconductor lattice. The process is given the name of doping, in which a small number of atoms of some other suitable elements are added as impurity. The doped semiconducting material are called extrinsic semiconductors. Inshallah, in your upcoming 17 chapters, which is about electronics, there you will study in detail about both the types of the semiconductor materials, that are P and N types. Now, here is a comparison among the three states of solid state of matter on the basis of their electrical conductivity. Conductors are those materials which can easily conduct the electric current. They have only one valence electron in their outermost orbit, and they are formed using the metallic bonding. Valence and the conduction bands are overlapped. Their resistance is very small, and they have a positive temperature coefficient. Some of the common known conductors are copper, aluminum, gold, etc. Semiconductors are those materials which conduct the electric current less than the conductors and greater than insulators. They are having 4 valence electrons in their outermost orbit. Semiconductors are formed due to the covalent bonding. Valence and the conduction band in semiconductors are separated by the forbidden energy gap of 1.1 electron volt. Their resistance is high. They can have a negative temperature coefficient. Commonly known examples of semiconductors are silicon and germanium. Insulators are those materials which do not conduct any current. They have 8 valence electrons in their outermost orbit. Insulators are formed due to the ionic bonding. Valence and the conduction bands are separated by the forbidden energy gap of 6 to 10 electron volt. Its resistance is very high. It has negative temperature coefficient. Commonly known examples are mica, paper, etc. Now we are going to quickly recap today's topic. The fundamental electrical property of solid is its response to the applied electric field, that is, its ability to conduct the electric current. The electrical behavior of various materials is very diverse. Some are good conductors, while the other are moderate conductors, and some are poor conductors of electricity. They are known as insulators. The conventional free electron theory based on Bohr model of electron is failed to explain the diversity in the electrical behavior of 3 types of materials. On the other hand, energy band theory is successful in resolving this problem. According to the band theory of solids, the energy level in an atom can be divided into 2 main bands, which are named conduction and the valence band. In case of insulators, we are having an empty conduction band, a full valence band, and there is a large forbidden energy gap present between conduction and the valence band. In case of conductors, the conduction and the valence band almost overlap, and there is no forbidden energy gap present. In case of semiconductors, there is a partially filled conduction band and a partially filled valence band at room temperature, and is a very narrow forbidden energy gap present. With the slight change or increase in the temperature, the valence electrons in the valence band get sufficient energy to jump across this forbidden energy gap and approach the conduction band. So in this way, the holes which are created in the valence band and the free electrons in conduction band are responsible for the conductivity in case of semiconductors. This is all from today's topic. Stay blessed. Take care. Allah Hafiz.